This screencast is about acids and bases and how they are connected to equilibrium. So we'll be focusing on finding the Ka and Kb for different reactions. Before we can get into the different types of equilibrium and how they relate to acids and bases, we first need to identify the differences between a strong and a weak acid or a strong and a weak base. So when something is labeled as being a strong acid or a strong base, it will completely ionize and form all the compound will break into the ions. So if we're talking, for instance, HCl, when HCl is aqueous, it will form completely H pluses and Cl minus ions. The same is true if you're dealing with a strong base. It will break into the two ions that make up the formula. When something is considered to be a weak acid or a weak base, it will only break into ions, leaving behind a true equilibrium where you have the original acid and then the ions. And how much of it breaks up depends on its Ka or Kb value. So the smaller the Ka and Kb, the less it breaks up into ions. You will need to memorize the strong acids and strong bases listed here. If it's not on this list of strong acids and strong bases, then it is weak, and we will be using it to solve for equilibrium. We will see a lot of net ionic equations. Now remember, net ionic equations are ones where you have, instead of writing NaOH, we would break it into its Na ion and the OH minus ion, and this would be in aqueous. So you're not going to worry about canceling and writing the net ionics, but you are going to see a lot of just charges as part of the reaction. Now remember, these are all in aqueous solution, and several times, most of the times, that will get dropped. So as you can see here, we have the self-ionization of water. We have water plus water making H3O plus and OH minus, and we use that equilibrium expression with our Kw. So our Kw is equal to the H3O plus ion times the OH minus ion. Remember that our Kw here is 1 times 10 to the negative 14th, and then you can solve for the various pieces. In an acid and base reaction, equilibrium is going to favor the transfer, so we're going to favor the transfer of a proton from a stronger acid to a stronger base. If you're given the choice between a weak acid and a strong acid, it's going to be the stronger acid is going to be the one that gives up its H plus ions. When we're talking about strong acids and strong bases, remember they completely ionize. So therefore, the weak acids or bases do not completely ionize. They will form an equilibrium expression. So we will have this generic equation here. We have HX. This is any acid. Here, we'll call this an acid. It's any acid. When it reacts with water in an equilibrium expression, it would form H3O plus and its conjugate base, which is just X minus. So if you were asked to write a K expression, remember you write the K by taking the products over the reactants. So you would take your products, which are H3O plus times X minus, all over HX. Now, the H2O cancels because we do not include solids, and liquids are not included in our equilibrium expression. So if you knew what specific acid you were dealing with and could look up the Ka value, they are listed in Appendix D on page and also on page 689 in your textbook. If you could look up the values, then you could solve for the concentrations, or you could solve for if you knew the concentration of the H3O plus, if you knew the concentration of this substance here, you could then take it and find pH. So a lot of the problems that we're going to be dealing with are either going to be solving for Ka or solving for one of the components of the equilibrium expression. A note here, the larger the Ka, the stronger the acid, or the larger the Kb, the stronger the base. Okay, so the smaller the number, the more weak they are. All right, here's a sample problem that you're going to use a weak acid and equilibrium. It says determine the Ka from the pH, and we are given that 0.10 molar solution of formic acid, HCHO2, with a pH of 2.38 at 25 degrees Celsius, and we're asked to find the Ka and what is the percent ionization. And you can see that we have an equilibrium expression here. So we're going to take our information that we're given and our plus, our H plus is, our H plus concentration is whatever the inverse of the log, so that's inverse of our log, 2.38. And so when we do that, our H plus concentration is 4.2 times 10 to the negative third. So I took my pH information and I used that to find my H plus. All right, so the next thing we're going to do is we're going to do an ice chart. So we're going to take our HCHO2, and that forms H plus, or H3O plus, and our CHO2, our conjugate base. And I'm going to use this in a nice chart. So, ICE. I know that I start with this much acid, and I know nothing about either one of these. And I know that they tell me that my pH of my solution is 2.38. Now, I have to remember that this is at equilibrium. When they tell me the pH, it's at equilibrium, unless they say it's initial, and they didn't this time. So I'm going to put in my 4.2 times 10 to the negative third here as my H plus concentration. Now you can finish filling in your ice chart with this information. We know that we increased by 4.2 times 10 to the negative third here and here, as well as here. And we know that we reduced by the same amount on my reactant. So whatever I subtract the initial and the change by, I end up having my equilibrium of 0.0958. Okay, so now I can find my Ka. My Ka is my products over my reactants, so 4.2 times 10 to the negative third. I'm going to go ahead and square that because they're the same value, all over my 0.0958. And that will get me an answer of 1.8 times 10 to the negative fourth for my Ka. Now I'm asked to find the percent ionization. And I do that by taking the concentration of the H plus at equilibrium, and I'm going to divide by the concentration of the acid initially, and then times 100. So that'll give me my percent ionization. So to do that, with the numbers we have, we're going to take our H plus at equilibrium, so 4.2 times 10 to the negative third, all over my initial acid concentration of 0.1. This is comparing what I had and what actually broke up, and then I'll multiply that by 100, and this one is ionizing 4.2%. So all you have to do is break the steps down, depending on what they're asking you and what they give you. Figure out the equation and put it into an ice chart and work it through just like all the equilibrium problems we've done in the past. Figure out what your change values are, and then how to apply it to the initial values, and plug it into your K expression. Remember, products over reactants, and make sure you do the math correctly. We will also be able to do problems where we will solve with X, just like we did in the past. Hopefully we can avoid the quadratic if possible, but if not, then we'll just have to use it.